Hi, this is Bob from INSYDIUM, and in this constraints tutorial, we're going to look at connections. We'll see how you can connect particles using springs and how we can adjust those for different behaviours. We'll also look at simulating soft bodies and how to set up custom springs between particles. So let's get started. In this scene, we've got an emitter, and it is set to a defined emission in a circular pattern with 5 count. What that's saying is we've got these 5 individually spawned particles in this regular distance apart, making this pentagon. We've got no speed, so they just stay where they are. So this is going to work well to demonstrate how we link these particles via constraints. In the display settings of the particles, I have display constraints highlighted and ticked, which means that when we have constraints, they will be visible. Okay, so let's go to dynamics and we'll bring in a constraint object. And we're going to use the connections, birth connections. So let's just tick connect at birth and resim and see what we get. So we have no constraints whatsoever. Why not? Well, what we need to look at is this radius figure here, which is set to 40 centimeters. And what this is saying is, for each particle, look within a 40 centimeter radius to see if there are any other particles. If there are, make a connection, up to 8 maximum with this connection limit. So what that's telling me is these particles are more than this 40 centimeters radius apart. So let's just check. We'll bring in a sphere. We've got this set to line view, and let's just move this sphere to the center of this particle, and let's reduce its radius down to 40 centimeters, which matches that constraint search radius. And we can clearly see there are no other particles within this radius, so there are no connections. So let's increase the radius of that circle so we can measure how far these particles are apart. There they are. So if we do it like 123 centimeters, these 2 particles are going to be within its grasp. So let's go back to the constraints, change that to 123. Let's resim. And now we have some constraints all the way around. And that is because the search area is big enough to find other particles to join with some constraints. Excellent. So let's just have a look. What I'm going to do is just doodle on here. So what's happening is if we look at this particle, we'll just colour it pink in the middle. This particle is looking in its search radius. Let's just move that sphere up to here. There we go. So what it's doing is looking for particles in its search radius. It's found 2. So it's made a connection to this one, and it's connected. And it's also made a connection to this one, and it's connected. All right. Now let's choose a blue colour, and let's look at this particle. Now this particle has a different search radius. That's not dark enough. This particle's search radius is obviously here. So it's found 2 particles in its search radius. So it's made a connection here. There we go. And it's also made a connection along here to this one. So you can see that these 2 particles are actually joined by 2 constraints because they are both in each other's search radius. And this goes on throughout the whole one. So let's just do one more. Let's move this search to this particle here. And we'll go the doodle. Let's make this kind of orange. So this particle is orange, and it's spied these 2 particles within its constrained search radius. Let's draw an arrow. That one's constrained, and that one's constrained. So again, these 2 particles are sharing constraints. There's 2 constraints, and this is going all of the way round. So that is the basics of how we use this radius to find particles. Now, let's make this a little bit more interesting and turn that doodle off. Let's make the search radius encapsulate all of them. So if you go to this sphere, so remember, we're just using this sphere as a measuring tool. It's not doing anything. We're just using it visually to see how big we need to make it in order to find our particles. So there, all of the particles are within this particle's search radius now. So let's just make that sphere invisible. So now if we, what is it? It's on 206. So let's change the search radius in the constraints to 206. Now we've got something looking very different. And that is because we have a connection limit of 8 particles. So any one particle is allowed to connect to up to 8 other particles if they are within this search radius. So now what we've got, let's do a new doodle. Now what we've got, let's look at this one here. So let's just take that and clear the frame. Right, so now what we've got, let's look at this one. So now, because our search radius is taking all of them in and it can connect up to 8 other particles, this one is connecting to this particle, this particle, this particle, and this particle. So it's made 4 connections. So in constraints, it can't make 8 because 8 don't exist. So if we change that down to 4 and resim, it looks exactly the same because it's going to connect to a maximum of 4, and every particle is going to do that. So if we look at this particle here, let's just change it to dark blue. So this particle has them all. It can connect to 4. So it's got 1, 2, 3, and 4. And so you can get these really interweaving patterns in your particles depending on how close they are to each other and how many are allowed to connect to each other at any one time. So that is how to use the radius and the connection limit to set up connecting your particles using these spring constraints. So let's take a look at what our constraints connections can actually do to dynamically alter the movement of particles. So in this scene, we have a plane which has got a collider tag on, and also these 2 cylinders which have collider tags on. And then we have an XP emitter above, and they're set to shoot out these particles on the first frame. We've got a gravity in the scene, so if we hit play, let's just get rid of that axis. If we hit play, the particles drop down and bounce on the floor, and some of them collide with the cylinders. Okay, so let's get some connections in here using constraints. So we'll go to the X particles menu. Let's press XP system sort, which will place our emitter and any other X particles objects in this system. And we will go to the dynamics tab and let's pick a constraints. So in the constraints, we want to connect these particles. Let's go to connections and we'll go to birth connections and we will connect at birth. And I'm just going to switch off braking for now. Just put no braking. All right. And let's just, so we can see these connections, let's go to the emitter, to the display tab and make sure that display constraints is selected, which it is. Okay. So now if I go forward a frame, we have got all of these constraints which have been generated. And that's because in the constraints object, we have connect at birth selected. So each particle is going to search within a radius of 40 centimeters and it will connect up to a maximum of 8 other particles. I'm just going to reduce that down to 6 so we haven't got as many. All right, so now we have these connections and it's not completely equal. Some have more connections than others. So now let's see what happens when we hit play. Without the constraints, the particles just fall to the floor. With the constraints, let's see what the difference is. Okay, so a very slight difference there. They're kind of holding together and trying to hold their shape. But let's say we want these particles to kind of stick to these cylinders. How might we do that? Well, what we could do, first of all, is go to the cylinders collider tags. And yes, we've got 100% friction on those and they're still not sticking. And that's because particles have their own friction value as well. So let's go to the emitter. Let's go to the extended data tab and the physical data. And look, we have an independent friction setting for the particles. So let's put that friction way up to, well, we'll just try it at 100 first. So that's interesting. The particles which have got the now got a high friction setting, maximum friction, have stuck to these cylinders, and we have what looks like a net because our constraints are holding these particles together. So that immediately looks like a dynamic, realistic simulation of these particles. Okay, so what I'm going to do, let's just leave that hanging, and I'm going to take this plane, make the axis visible with Alt-D, pull it down, hide that axis again, and I'm just going to hide the logo of the X particles system from the viewport. So now we have these hanging constraints. If I go to my constraints object, let's reduce the stiffness of those constraints and see what happens. So they're starting to stretch. Those springs holding the particles together are able to stretch under the constant force of the gravity modifier. And if we put the stiffness way down, they're slumping all the way to the bottom. They're not breaking because we have deselected the breaking option. And if I increase that stiffness, they'll spring back up again. So that's interesting. Just by selecting and getting the friction of these particles to stick to the cylinders, we are getting this really nice kind of constraints simulation of this net of particles. And if we brought in another modifier, let's bring in a motion modifier, and we could bring in a wind, for example, and now we can see that the wind is blowing those particles. And let's put the strength way up. We could even add a little bit of turbulence. And we're getting this dynamic simulation. And that's the wind is too high for the particles to even land. And there we go. There they go, flapping about the place. Increase the wind strength. We could bring the scale of the turbulence way down, but have more turbulence. And then it's really being wafted around the place. But the constraints are holding those particles together. If the force gets too great, it will pull them off these cylinders because they're not actually stuck. They're just gripping with their friction. We've got to the point where we've only got one left. So that's interesting. Very, very quickly, let's get rid of that wind. Very quickly, we can have this dynamic simulation using constraints birth connections. So what else can we do with this? Well, we've seen with the stiffness, we can make it more floppy, give the springs more stretchiness, or make them more rigid. What you can see is if we put this stiffness way up to full rigidity, and we can make them even stiffer by going to the project settings. If you hit Control or Command D, it brings up the Cinema 4D project settings, and there is an X Particles tab. If we click on here, we have got subframe steps and iterations for X Particles. Now, the rules with constraints is this: the more iterations in the solve, the more rigid the springs will become. So if I increase my subframe steps up to 3 subframes per frame, that means there's going to be 3 times the iterations, and you can see that these constraints are now much, much more rigid. Let's go to the constraint and bring that stiffness way down, and look how much we've got to reduce that stiffness to get them to stretch at all. And that's because we had stiffened them up further using the Control or Command D and then adjusting the X Particles subframe steps in the project. So that is important information to know. So now let's have a look at braking. So at the moment, these can stretch and stretch and stretch. Even if they have no stiffness, they'll stretch to the floor, but they will never break. However, we can alter that. So let's give them, say, 5% stiffness, resim. So there are our constraints. What if we wanted them to snap? Well, what we're able to do is use one of the braking modes. So I'll tell you what, for this, what I'm going to do is just turn down those subframe steps back to the default of 1, because it just gives us a little bit more, it's a bit easy to control this stretching. So let's have a look at these braking modes. So brake as none means that the constraints will never break, and they'll just stretch and stretch and stretch, and they'll never change. However, we've got 3 different braking modes. The first mode is the one that's on by default, and this is called relative connected. And what this does is this. I'm just going to spawn the particles and stop. And then let's look from the top view. So what this is going to do is I'm just going to hide the plane and hide the cylinders. So here we have our particles. So what relative connected is going to do is this. Let me just take my doodle. And let's just say that we are looking at this particle and this particle, which have formed this constraint. Okay? And what relative connected does is it uses this percentage. And what it means is this. If this particle were to move up more than 50% of its original length, then the constraint will break. So this is its original length. So if it were to move 100% of its original length, it would move up to here. If it was to move 50% of its original length, it would move to there. So that's the breaking point. If this particle moves this direction beyond this line, this connection will break because it's been stretched too far. So let's just have a look at what that might look like in our scene. So we'll go to, let's make all of this visible again. And I'm going to increase the rigidity. So let's press play. And they've fallen and broken. So these ones here have remained on our cylinder and the others have broken. And that's because they were so stretchy, they easily moved 50% of their original distance and they've broken. So let's increase this to say 200%. So they gripped for a little bit. Look, let's just go in frame by frame. So they've attached. They've started to stretch. They haven't stretched beyond 200% of their original length. Still haven't. And one of them is going to snap pretty soon. There. So this one here, these two particles have moved apart over 200% of their original distance. And therefore, the connection has been broken. And if we go forward again, more have broken until the sim equalizes and they drop off, and these ones are then left hanging. So the good thing about using relative connected as the breaking method is that, like in this scene where we've got some constraints which are longer than others, it's going to base it on its original length, which is good. So let's change that and go to another mode. Let's go to the relative radius. Now what this is going to do is it's going to look at the search radius, and if a particle moves away from each other more than 200% of this search radius, then it will break. So 200% of this search radius is 80 centimeters. So if a particle moves more than 80 centimeters apart from its joined particle, the connection will break. So let's have a look. Okay, so they're not moving far enough to break. So let's reduce that down to, say, 150 and see if we get a break. Still no break. Let's go to 100. So they're not moving more than 40 centimeters away from each other with the constraints set up as they are. Let's move it to 50%. So now they only have to move 20 centimeters more away from each other. Not even that. Let's go to 20%. Still none. Let's go to 10%. And we're getting our first break. So 10% of 40 is 4 centimeters. So they're moving 4 centimeters away from each other, and we are getting our break. So relative radius is similar to relative connected, but it measures it on this original radius, search radius amount, not the original constraint length. And then the final mode is just an absolute distance. If they move more than 60 centimeters apart, they will break. So this is going to create no break at all. We need to go down to about 10. That's obviously too much. 20. That's a little bit too much. They're joined, but they're breaking a bit too easily. Let's go to 30 centimeters. And then we're getting a bit of a break. Let's go to 40 centimeters. And then they snap and break. So we've got 3 different braking models, all of which work in similar ways, but they give you that ultimate control to get your braking working as you require. So that is the basics of connecting particles at birth, adjusting their stiffness values using the stiffness slider, but also the project iterations, and then also how some of these various different braking models work to get our constraints to snap and allow particles to break off from the main body. So let's explore our constraints birth connections a bit more deeply. We'll bring in a constraints object into our X-particle system hierarchy here, and in birth constraints we will hit connect at birth. Let's leave everything as default apart from, we'll remove the braking. So let's set the brake as to none. So what we've got here is this box emitter in our seed, and let's have a look in the emission tab. We've got the mode set to regular. So what that's going to do, it looks at the particle radius and it tries to fit as many of those particles of that size into the volume of this box in a regular grid. So if we go forward 1 frame, there we can see our 4 centimetre particles put into this perfect grid. If we put 3 centimetres and respawn them, there are more particles as more 3 centimetre particles can fit within that box volume. Let's put it back to 4. And as we can see, because we're viewing our constraints, we can see that our birth constraints have been created here. And let's just remind ourselves how it works. We have a radius of 40. So each particle searches within a radius of 40 of itself. And if it finds another particle, it makes a connection up to a limit of 8 connections per particle. So that's what we have. So we've also got a gravity in this scene. So if we hit play, let's see what happens. And the particles fall down. They remain connected because we've switched off braking, but they haven't really kept this volume of this box object. So there's 2 reasons why that is the case. One of the reasons is that the springs, these connections, aren't stiff enough. So if we put the stiffness up to 100%, it's still not going to be stiff enough. But what's the other way of making our constraint springs more stiff? Well, it's to up the iterations per frame. So we go to the settings for that within our Cinema 4D project settings, which is Control or Command D. So we get our C4D project settings, and there's an individual X particles tab here. So let's click on that. And we've got the default subframe steps as 1 and the default iterations as 3. So what I'm going to do is I'm going to increase the subframe steps, which means that we're going to have more iterations per frame as well, because obviously originally there's going to be 3 iterations per frame, and now there is going to be 3 iterations per subframe, so there's going to be loads more. So let's have a look. These should be stiffer now. Okay, there we go. So it's holding together much better. Now we've increased those subframe steps. Excellent. So the other reason that this is collapsing a little bit is because the particles are able to intersect each other. You see these 2 here are virtually on top of each other. And that is because we don't have any particle-to-particle collisions going on. So we're not telling the particles you're not allowed to intersect. Well, we can do that using constraints, because if you look next to the Connections tab, there is a Collisions tab. So let's go there. We will activate collisions, and now let's see what happens. So now we should have a double whammy. We should have the constraints stiffness trying to keep these particles apart, but also we have our constraints collisions, which are stopping them from intersecting. So now we should get a much better, more kind of rigid soft body box. Let's have a look. Great. All right, so that's looking really nice, isn't it? And it really gives the illusion of a soft body box, even though these are lots of separate particles. They are connected by constraints, and they're also not able to intersect. And you can see that we're getting the illusion of a soft body. That's working really, really nicely. So let's just alter some of these settings and see what we can do with that. Let's go to the connections. Let's reduce that stiffness a bit. Now that we've got those collisions on, let's see if reducing that stiffness does everything. So you can see it flopping down. And so now it's a much more floppy soft body. And if I quickly whack up this stiffness, you'll see it'll pop back into its shape. Watch. Pop. And there it goes. Okay, so we can make it even more stiffer by adding more springs. So we've got a connection limit of only 8. So let's put 50. So we've got 50 connections. And you can see we've got lots more constraints now. And you can see that it's still going to be springy, but it's kind of springing back into shape more quickly because it's got more constraints. Let's put that up to 100. And now it's really tightly sprung because we've got loads of connections in there. So that's interesting. Let's put that back down to 20 so they're not quite as... I prefer it a little bit more bouncy. So that's really cool. What else could we do? Well, let's try adding another emitter, because this will lead us nicely into why we would use distance constraints rather than birth constraints. So what I'm going to do is get my emitter, and I'm going to hit Command and hold it and drag to make a copy. And then the copy I'm going to pull up a bit, and let's just rotate it around so it's different. And do you know what? In the copy, I'm going to go to my display, and these are being coloured by a random gradient. So each particle is randomly given a colour anywhere on this gradient. Let's just change that. I'm just going to take those knots out. And in the blue one, let's just change it to a light green. Okay, so the top particles are actually, let's bring that right down. Okay, so the top particles are kind of the greeny ones, and the bottom particles are the bluey ones. So now we have only one constraints object, but 2 separate emitters with constraints at birth. Let's see what happens when we let this sim run its course. Let's have a look. So now we have got 2 separate soft bodies interacting with each other. So that's fantastic. Looks great. So before we move on to the second connection type that I want to show you, which is distance, I just want to demonstrate how you might, if you want to create a very fast simulating, simple soft body bit of geo, we can use this technique. Let's just get a generator, and we'll pick an XParticles OpenVDB mesher. And the mesher asks for what's the source, what object do you want to mesh? So let's drop in my first emitter. And it's very blobby. Let's just hit ND to see the lines. So it's very blobby. So what we could do is reduce this point radius, which is the radius around each particle. So let's put that way down. And then let's add a bit of filtering. I'm going to switch on filtering. I'm going to get rid of median, and I'm going to bring in a Gaussian filter. And that'll probably do for now. So let's just play that. So now we've got one soft body. Very good. And we could probably just, for speed of simulation, I could increase this voxel size. So there's less definition here because I've got fewer polygons, but it'll run just that little bit more quickly. Okay, so that's good. So let's just hit Control and copy that OpenVDB mesher, delete the emitter, and drag in emitter 1, the other one. So now we've got 2 soft bodies. Now there's one problem with this. And can you see that they're actually intersecting? And that isn't anything to do with the OpenVDB mesher. That's because these particles are slightly intersecting. And the reason that they are intersecting is that we don't have enough subframe steps to accurately be able to work out the collisions because they're moving so quickly. So between subframe steps, a particle has already moved on top of another particle, and so it doesn't know that it needs to push it away. So the only way to make that more accurate is we go back to Control D or Command D, and we need to increase the subframe steps. I'm going to put that up to 10, and I'm hoping that that is going to be enough to sort out those collisions. Yep, and now it's bouncing on top without any of those intersections. Very nice. Let's just activate our meshes again. And there we go, and they're not intersecting, and they're kind of wobbling all over the place. So for very kind of fast simulating, simple soft bodies, these constraints are giving us a lot of options, and for some scenes, these are going to work absolutely fine. Okay, so let's just get rid of those meshes for now. So now we can see that we've got our 2 separately interacting soft bodies. But what if we wanted them to stick together? once they hit each other. Well, we're not going to be able to do that using, let's go back to the constraints object, using our birth constraints, because they are only calculated once when the particles are born. But what we want to do is use a connection type that's always been calculated. So when particles from even different emitters come close to each other, they can then start to join and create more constraints. So this is where the distance constraint comes in. So what I'm going to do is switch off the birth constraint, and I'm going to bring in a distance constraint. So let's click connect within distance, and we get what look like very familiar settings. We have a radius amount, so the particles are going to search within this radius for other particles, and then we've got a connection limit. So if I hit play, our simulation looks exactly the same. So why aren't they connecting? Well, each particle has already reached its connection limit. Each particle must have 8 particles it's joined to. So by the time these emitters get close enough to join, they've already reached their limit, and so they can't join. So let's increase that connection limit up to, say, 50. Right. So with a connection limit of 50, these particles have managed to join with each other. So that's telling me 2 things. It's telling me that the search radius is a little bit too big, because I don't want these to be joined before they hit further down in the scene. So one thing I could do, I could either reduce this search radius, let's put it at 20, so now they're not joined, and if we hit play, let's just go down slowly. When they come near to each other, now they have joined. So if we play that, let's see what the result is. Let's just hide that axis. And now they're joined. But they've joined with quite a long constraint, haven't they? Which is not necessarily what we want. So what we could do is put that radius way down to 5. Okay, so that's not enough. Let's put it 10. There we go. And now they're stuck together. You see, they're stuck, and these have stuck together and become one object. So that is really interesting. We've managed to attach them together. And that is because the distance constraints, this search radius, they search every single frame to see whether there is a particle within the distance. And as long as there is enough particles in your connection limit, it will connect those particles. It doesn't matter what emitter they're from, whereabouts in the scene, when they were birthed, they will always connect within that distance. So that is really useful. Okay, and the way in which the breaking works within the distance constraints is slightly different. You see, all you're given is this percentage. If the percentage is on 0, it means there will never be any breaking at all. But if we increase this, it is using this radius value. So if I put this at 10%, what it's saying is if 2 particles move away from each other more than 10% of this radius, so 10% of 10 is 1 centimetre, then they will break. So let's just see at 10% whether we get any breaks. And we have, look, they've broken in half. So that's quite cool because they have moved in that amount. Let's make it a higher threshold to see whether they hold together better. Okay, so only these ones have managed to break. The ones underneath that have hit the sphere. And they're breaking. Let's do slightly less, 14%. And now we're getting these really interesting breaks as they're snapping in half. We'll put that stiffness up maybe. So as you can see, we can either use distance, we can use birth, and that's they work in similar ways, but the advantage of distance is that it's always looking within this search radius on every frame for any particles that may be in the area and could be connected as long as you have enough in your connection limit. So let's have a look at the final connections type within constraints. Let's bring in a constraints object. We'll go to the connections tab, and we have custom connections, which is an incredibly versatile and powerful type of constraint. It doesn't have that many settings, but some of them feel a little counterintuitive at first, and there are some gotchas with this. So let me just talk you through this scene. This is how we're going to demonstrate how these work. We're in wireframe view at the moment. Let's just press ND to show the polys and lines. So I have this tube, which is just a cylinder, and what we want to do is trap some particles inside this tube. So we've got a X particles collider tag set to inside. All right, so that's the tube. I'll just make that invisible. And inside, I've got another smaller cylinder. This one at the top is called pusher top, and it has another collider tag on with connect on collision active, which means that when this particle is born, it's stuck immediately to this pusher. And then I have another one called pusher bottom, which is this little cylinder here. And this has a collider tag on as well, but this doesn't have connect on collision. And what this allows us to do, this setup, I'm just going to press NG for the wireframe. What this allows us to do with this gravity is, if I move this pusher bottom up and down, I'm able to manipulate these particles. Okay, very good. So in the constraints object, I'm just going to put collisions and make those active. And that means that if I push that particle up, it'll bounce off the top one. Great. So now what we want to do is have a look at how we connect particles using the custom connections mode. So let's just activate this. And the weight we'll have at 100%. We're not blending this connection with any of the other connections, so we'll just leave that at 100. The connection limit works in exactly the same way as we've already explored in birth and distance connections, so just put that down to 1. We've only got 2 particles. We can only make 1 connection, so we may as well just have the connection limit at 1. And then we've got this connection radius, which again is exactly the same as what we've explored in birth and distance. When the particles are within 30 centimeters of each other, they will connect. So let's just make that a bit bigger. I know that this tube is about 400 centimeters, so let's make this 200 centimeters. So, I mentioned that there are a couple of gotchas when you're using custom connections, and the first one we can explore immediately. So if I get my bottom pusher, what should happen is when this gets within 200 centimeters of each other, it should make a connection. And there is our connection. All right. But we've got a problem here. If I move that down, it just disappears straight away. Why is that? Well, that's because both of these settings, compression and expansion, have their own break values. So before I even explain what this does, let's just put the break values to 0. So this constraint is never going to break. Okay, and now we're able to adjust it, and it's not going to break. And the next thing I'm going to do, which at the moment won't make sense, but I'll explain this to you in a couple of minutes' time, is I want to adjust this plastic level so that it's not having any effect on the scene for now. So to do that, I'm going to set the compression plastic level to the smallest number possible, which is 0, and the expansion plastic amount to a really massive number that's going to be so massive it'll have no impact on our scene. And that will make sense a little bit later. So now what we have got, if I put my pusher bottom, now we're getting a connection. It's connecting within 200 centimeters of each other. And this is what's happening with custom. We have a compression setting and an expansion setting. So let's just get a doodle and let's draw in this. So this is what's happening. When these particles are 200 centimeters away from each other, as they are here, they create a constraint, joining them together. And that constraint is like a spring. And here is why custom connections are really cool. The compression settings are what happens when the let's have a look. When the particles are moved closer together and the constraint is compressed. So let's just draw that in. So compression happens when these particles become closer together, and that constraint becomes much tighter because it's been pushed together in that kind of way. So that's what the compression side of these settings do, and they dictate how stiff that spring is when it's compressed. And then the other type, obviously, is the reverse of that. And this is when the particles are stretched out. Let's have a look. When that constraint is made much bigger, because they're being stretched outwards, they're being expanded upon, the spring becomes more pulled out. And that is what our expansion settings do. So we have a stiffness of spring when the particles are compressed, and a stiffness of a spring when the connection is being expanded. And that is the key concept to get your head around with our custom connections. So let's just clear all of those. Okay, so at the moment, we're not really getting much bounce with it. If I hit play and knock that up, it kind of falls back down with gravity, but we're not really getting a springy kind of up and down motion here. It's just stopping. The gravity's being pulled down and it's stopping. Stop. Stop. So let's have a look at how we might adjust that. Well, at the moment, the compression stiffness is set to 60%, which is actually very stiff, and the expansion stiffness is set to 80%, so it's really hard for this spring to expand. And what you'll find is, what I'm going to do is, at the moment, we have a fall-off value of cubic, which means that this stiffness is applied to the radius, to the length of the constraint in a cubic way. So we've got a curve that applies in this fashion along the length of that connection. Whereas if we change this to let's just change it to flat, then we're not going to have any fall off at all. It's just going to have across this entire radius exactly the same stiffness in both compression and expansion. So that's going to make it easier to demonstrate. So again, though, if we go to this push bottom, nothing's happening. And that's because you will find that most of the variability of the stiffness of the expansion and the stiffness of the compression is found at the lower register of these percentages. It's not really a linear slider, this. So if I even put these back down to really low, 27, we're still not going to get any kind of bounce in compression and expansion. It's just the gravity's pulling it back down to the 200 centimetre connection, and there's not really any springiness. So let's bring that down even further. But at 1%, so at 1% are we going to get any springiness? So we are. So now at the lower register, with an expansion stiffness of 1%, it's able to stretch out before it gets pulled back in. And with a compression of 1%, it's able to compress back up again before it gets to its equilibrium. So let's go even lower. Let's go down to 0.1 and 0.1. So now we're getting real springiness. So you can see that you have to be careful here with these compression and expansion stiffnesses. It really is at the lower end of this register when you're seeing changes in this sim. But now we have got this, which has equal amounts of compression stiffness and expansion stiffness. So if I put the compression up to, say, 5, this means that it should be able to drop down and expand easier, but as it gets inside of the 200 centimetres, it should be harder, so it shouldn't jump back up as easily. And you can see it's halting it. And we're getting some weird movement, and that's because really what you need to do is keep these in relative equilibrium. Otherwise, you're not going to get a steady compression and expansion of your springs. So you kind of usually, in most cases, you want these to be of similar values. And there we've got this nice compression and expansion. Okay, so that's how your compression and expansion settings work. So now each has their own break value, and this is very useful. So the compression break value is how far it is able to compress before the connection is lost, and obviously the expansion is the opposite of that. So if I put the compression break value to, say, 50 centimeters, once this constraint gets within 50 centimeters, it should break. And there it goes, it's broken. But because we've got a gravity in the scene, the particle's going to fall back down, and it goes outside of that 50 centimeters, it re-establishes contact again, now with a new connection radius. And it drops in again. It drops in again. So that's how that connection works. If we just, let's respawn. If I put a connection break of 100, now it'll break more quickly, and there it goes, it's broken. And it'll join up again, and it'll break. And it'll join up again, and break. And you see, when it breaks and rejoins, it's given a new connection limit. Okay, good. And obviously, the expansion works on the opposite. Once it's expanded so far beyond this amount, it will break. So, let's just take the break out, because that's pretty self-explanatory. Now, we're going to talk about this plastic level. So what plastic means is this. If it is, we'll look at just the compression for now. If our constraint gets compressed so much that it goes beyond what we set here in this plastic limit, it is no longer able to compress any further. It loses its springiness. So let's just have a look at that. I pull my... Okay. And it'll no longer be able to come back out to its original length. So let's put this at, say, 100. So let's see what happens. So we're going to compress it beyond this 100 centimeter limit, which means now if I bring this down, it's now lost its ability to uncompress and come back to its original point. So it's got shorter and shorter and shorter, the constraint length. Let's just do that again. So we bring it up to within 100, bring it down, and it's unable to come back and uncompress, so it's compressed forever. It's become plastic and it's lost its ability. And if you imagine this, when you're a kid playing with a slinky, and this would be the expansion plasticity. If you stretch your slinky out so far, it gets to the point where it can't pull itself back in again. It's stretched forever and you've ruined your slinky. So that is what the plasticity does. The compression doesn't allow it to decompress, and the expansion plasticity doesn't allow it to recompress back to its original length. So that is relatively self-explanatory, but the rate can be a little bit difficult to understand. And the rate is how quickly does it become plastic? So if you have your rate very high, let's say 99%, as soon as this particle has moved within that 100% plastic rate, it'll become plastic. And so you won't notice much change. It becomes plastic immediately. And so it looks like it's become plastic too quickly. Whereas if we put it down to 1%, it can travel up further before it becomes plastic. And so it'll become much shorter with a lower rate, because it's only becoming plastic. It's able to travel further before it becomes plastic. Now, intuitively, I think it feels like that would be the other way round. But actually, logically, it makes sense, because it's not becoming plastic as quick. It's taken longer to become plastic, and then it becomes plastic, and the connection ends up having a shorter distance. It resets, and this is the new constraint length. So when your rate is high, it will become plastic much more quickly, meaning the new length won't go up as high. Whereas if your rate is 1%, so it becomes plastic less quickly, it means it can travel up higher, which means you get a really short plasticity length, and the new length is super short. So yeah, you think of the rate. If it becomes plastic more slowly, it means that the new constraint is going to be much shorter because it's able to travel up further before it becomes plastic. If the rate is 100%, 99% much higher, it becomes plastic very quickly, which actually means that it becomes plastic as it gets to kind of this point. So your new constraint level will actually be longer than it would be if you had a shorter rate. And obviously the expansion works it's on the inverse. This is when the particles are moving away from each other. So that is how our plasticity works. If we put it down to 0, obviously it never becomes plastic on that compression, and it's always going to pop back together. So that is the basics of how the various different settings work in our custom connections. It gives you the compression settings, it gives you the expansion settings. We can have individual break values for each, and also these individual plasticity values for each, which changes the overall length of that constraint if it has been compressed or expanded too far.